Welcome to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. My name is G. Sampath. I am going to explain the subject VLSI design. Today, we are going to discuss the topic 0-1 detector. It is a data path subsystem, right? 0-1 detector. 0 or 1 detector. We can detect 0 or 1. Okay, large number of inputs. Okay, in this used large number of input, large number of large number of input, ones or zeros, ones or zeros can be detected. So ones or zeros detection, right? Detection. So more number of fan in, more number of fan in, in this 0-1 detection, 0-1 detector. So more number of fan in this, more number of fan in this 0-1 detector, right? So by using this effective hardware design, effective hardware design, because similar number of data we are taken, effective hardware design, by using the speed increases, okay, by using the speed increases, okay, low power design, reducing low power and effective hardware design, more number of fan-ins. So we can take like a 16-bit, 32-bit and 64-bit data also we can take in this 64-bit data. More number of inputs, large number of ones or zeros can be detected. It is called as 0-1 detection. Okay, 0-1 detection, right? 0-1 detection. Now let us see the circuit diagram of this one. 0-1 detection. It can be designed by NAND gates, right? NAND gates. Okay, you see this one now. So this is one NAND gate. This is one NAND gate. This is also one NAND gate. This is also one NAND gate. This is also one NAND gate. So from here to we can connect one more gate here. From here to one more gate here. Okay, you can see this one. Okay, a bubbled AND gate, right? Okay, a bubbled AND gate here. You can see this one. The output of this one goes to one AND gate. Okay, right? You can see. So from here we can directly connect the output one AND gate. Okay. So this is bubbled AND gate. Bubbled AND gate. Let us see this one. How inputs are 1, 2, 3, 4, 5, 6, 7, 8. Let us take this A0, A1, A2, A3, A4, A5, A6, and A7. Right? It is 8 number of inputs. 8 number of inputs. Okay, 8 number of inputs. 8 number of inputs are here. If you are applying all common input is 1. If you are applying all common input is 1. Detecting 1. So this is 1. Okay. This is 1. This is 1. This is 1. And this is 1. This is 1. This is 1. This is 1. And this is 1. You see. So 1 complement is 0. Okay. And 1 complement, NAND gate, 1 complement is 0. 1 complement is 0. 1 complement is 0. Now what happens? 0 complement. 0 bubble is here. This is 1. This is 1. Okay, this is 1. This is 1. So output is 1. Output is 1. So as a input, output is equal to 1. So output is 1 detection. Okay. So it is 1 detection out, 1 detection circuit. 1 detection circuit. Okay, one detection circuit. So the circuit diagram, it is one detection. Okay, one detection circuit, one detection logic gates. Okay, one detection by logic gates. So what are the logic gates here? We are using NAND and NAND gates and AND gates. So NAND and AND gates. NAND and AND gates are used. NAND and AND gates are used. So common input. All common inputs are 1. So 1 input. 1 as a input. 1 as a input. It is 8 bit. We can say it is a 8 bit. So large number of, you see how many fan-ins are here? How many fan-ins are here? 1, 2, total 8 inputs are here. So it is 8 bit, means fan-in 8. Okay, fan-in 8. So it is fan-in is 8. So fan-in is 8. So how many fan-outs are here? Fan-out is 1. Means as a input we can, so output is only 1. As a, from this we can use so many number of outputs. So from this we can connect as a fan-out, as a input to this one. So large number of fan-ins are used. Large number of fan-ins. We may also use, also inputs are also we can take input. We can take input 16 bit, 16, 32 bit and 64 bit data. 64 bit. Large number of fan-ins are here. Only single common input is taken. Then here 1 is given, output also 1 detection. Okay, 1 input is given, output also 1 detection. Let us see the another one. If you are taking 1, then output is 0. 1 detection. Let us see the 0 detection also. Right? 0 detection. Okay. So this is again one bubble AND gate. Okay. One bubble AND gate. So from here we can take the output over here. Right? One AND gate. One AND gate is taken. Okay, you can see this one. So the input is bubble over here. Bubble over here we are applying. Okay. So how many inputs it is? 4 inputs. A0, A1, A2 and A3. So it is 4 bit 4 bit input. Okay, 4 bit input. 4 bit input. We can say fan in. How many fan in? So fan in is 4. So fan in is 4. If you are taking all inputs are 1. All inputs are detection 1, 1, 1, 1 and 1. Now what happens? One complement is 0. Okay, this is 0, this is 0, this is 0, this is 0. So output is 0, output is 0. So 0 and gate, it is 0. So it is 0 detection. So it is 0 detection, 0 output detection, 0 output detection. You can see 0 output detection. It may be 1 or 0. Large number of fan-ins. Effective hardware design. It is used to low power design. So it is by using the 0 1 detection, large number of fan-ins, low power design and fast data can be transmitted. So output is 0 can be taken. It may be output 0 or 1. So it may be, if you are applying instead of 1, if you take 0, then output will be 1. Output will be 1. Here also, instead of this 1, if you take 0, 0, 0, 0 over here, then output will become, it will be 0. Okay, so 1 input, output also 1. But here 1 is taken, output is 0. So according to the design, right? According to the design. So it is 0 detection. 0, 1 detection, but output is 0. Okay, this also we can take 1 detection. 1 detection, 4 input data. 1 detection. 1 detection. 1 detection. 4-bit logic design. 4-bit logic gate design. Logic gate design. Okay. Okay. So we can also call this as large 1 detection. We can also call as LOD. LOD design. LOD means large 1 detection. Large 1 detection. Large 1 detection. Large 1 detection means large 1 detection means we can use more number of ones or zeros. Large number of fan-ins. It may be 1 or 0. It may be 1 or 0. Right? It is effective design, fast design, low power consumption. Okay. Let's see the another way of design. 1 detection. The another circuit. If you take this one, let me take this one AND gate. One AND gate. This is A0, A1, okay, A2 and A3, A0, A1, A2, okay, A2. We can take here one inverter, okay, A3, and we can take this A4, okay, and A5 and A6 and A7, okay. So this is again one NOT gate. This is again one NOT gate and output of this one. Okay, so first it is also 1 detection. From 1 detection, this is an AND gate, and from here, which is connected to one gate, bubble AND gate. Okay, bubble AND gate. Okay, you can see this one. This is one bubble AND gate, and from here again one AND gate. Okay, one AND gate. Then from here again, this will be given to one more bubble gate. Okay, one more bubble gate. Okay, and this path is connected to one more NAND gate design. Okay, NAND gate design, and from here you can connect another bubble AND gate, more number of fan-ins. Okay, So the final one which will be connected to the AND gate, final AND gate. Final is the AND gate. Okay, the final is the AND gate. So the how many inputs are here? It is a 8 input again. So it is 8 input, 1 detection. Okay, 8 input, 1 detection circuit. 1 detection circuit. Okay, 1 detection logic gate. Logic gate design. Okay, logic gate design. Okay, let me take the inputs are 1 over here, 1 over here, 1 over here, 1 over here, 1 over here. Let me take the what is the output over here. So here it is a NOT gate, the NOT gate design. Okay, now what happens here? One complement is 0, one complement 0, one complement 0. What happens? 1 into 1 complement is 0, 0 here, 0 complement is 1, 0 complement is 1. Okay, okay, the one over here, then complement is 0. 1 over here, complement is 0. Now what happens? It will be 1. Now 0 complement is 1. Again 1. Complement is 0. Okay, another input is 1. Okay, 1 into 1, 1 complement is 0. 0 here, it will be 1. Now 0 over here, it will be 1. Now 1 over here. Now what is out? Again output is, AND gate is 1 detection. So output also 1. So this is final output. Okay, so all ones, output also ones, all input ones, all input ones, all input, all input ones, output also 1, output also 1, output also 1. Okay, output also 1. And previously all inputs are 1, output is 0. So 0 output, 0 output, right? So any one detection, then output may be changes. Okay, so let us take the another mass transistor design also we can take. Okay, for example, so now we are applying it is NMOS are in parallel, NMOS in parallel. Okay, NMOS are in parallel. Okay, right, NMOS are in parallel, and PMOS is here. It is a pseudo NMOS design, pseudo NMOS design, pseudo NMOS are design. So we can design this pseudo NMOS design, right? Pseudo NMOS design means PMOS transistor across this PMOS, then this is connected to ground potential. Pseudo NMOS design. So this is PMOS transistor, pull downs are NMOS transistor, A0, A1, A0, A1, A2. So it is 3 input. Okay, 3 input, 3 input fan in. Okay, 3 input fan in, 3 input fan in. Now output is, then output will be taken. Okay, this is output is, and this one is output now. Now VDD and VSS, VDD and VSS. Okay, now A0, all inputs are common. All inputs are common means only single input. A0, A0, A1, A2 equal to 1. Now tell me what happens. A0, A1 equal to 1. Right, A0, A1, A2 equal to 1. Now what happens? This will be 1 and this will be 1 and this will be 1 more. Now what happens? So the circuit is closed. Okay, the path established from here to here. Path established from source to drain. Gate voltage is 1. Gate voltage is 1. Path established. So here PMOS is on. PMOS always on transistor. Now VDD directly connected to ground potential. VDD directly connected to ground potential. All inputs are 1. Output is, then output is 0. Okay, 0 output. 0 output. Okay, A0, A1, A2, A0, A1, A2 equal to 1. Equal to 1. Only one detection. Okay, one detection. It is one input. So one input detection. So it is called one input. One input means it is logic one input. One input detection. One input detection. One input detection. Okay, one input detection. That is logic one. So that is logic one we are applying as a input. That is logic one we are applying. Logic one we are applying. What happens? So gate voltage is equal to 1. NMOS is on. NMOS is on. NMOS is on. Now here it is always on. Pseudo NMOS means PMOS is a depletion mode means pull-up transistor. These are the pull-down transistor, parallel connections. On means path established. So the VDD directly connected to the ground potential, output will be 0. If we are applying, if A0 equal to A1 equal to A2 equal to 0, if you are applying 0 as a input detection, 0 as input detection, 0 as input detection, all inputs are 0, then what happens you can see. So if you are applying 0 over here, if you are applying 0 over here, if you are applying 0 over here, for logic 0, this is open circuit, this is open circuit, this is open circuit, this is open circuit, 3 are open, then output is equal to 1, then output is equal to 1 output. Okay, so output is logic 1, output is logic 1, output is logic 1. So this is about the pseudo NMOS 0-1 detection. Pseudo NMOS, this is pseudo NMOS 0-1 detection, 0-1 detection circuit, 0-1 detection circuit, detection transistor representation. Okay, detection mass transistors, okay, mass transistors in parallel way. We can also design this in series connection. Okay, let me go and explain this in series connection. What happens? For example, more number of fan-ins we are applying. So because of this, because of NMOS transistor parallel, it is a OR gate. Okay, so it is like a 3 input. Let me take this one. Okay, so input we are applying, it is a pseudo NMOS, it is a PMOS. So A, B and C. Okay, A, B and C, series connection. Okay, so this one is a VDD and VSS, and this one is output. This is output signal, this is output. Okay, so it is a pseudo NMOS. What is pseudo NMOS? Pull-up transistor is, this pull-up transistor is PMOS transistor. All these pull-down transistors are NMOS in series. Okay, NMOS in series. Right, NMOS in series connection, and these are the series connection or parallel. Previously we have seen parallel connection. Now pull up is PMOS transistor. Now pull down is series connection. Pull up is again PMOS. Okay, PMOS is grounded connection. So it is always on transistor. Now if you are applying ABC in how many fan ins are here? How many fan ins are here? 3 fan ins, 3 inputs, 3 fan ins, 3 inputs. Okay, fan in equal to, so fan in equal to 3, fan in equal to 3. We can increase a more number. We can increase a more number. If A1 is equal to, A1 is equal to, sorry, A is equal to, B is equal to, C is equal to 1. If you are applying 1, common input is 1. Okay, common input is 1, we are applying 1, 1, 1, we are applying. Now what happens in this? So then this will be on transistor. This will be on transistor. This will be on transistor. Right? Then VDD directly connected to ground. Directly connected to ground. Then output voltage is equal to 0. What is output voltage? It is 0, grounded connection. If ABC is equal to, if you are taking ABC equal to 0, ABC equal to 0. Now what happens here? 0 we are applying. Now we are 0 we are applying. Now 0 we are applying. 0 we are applying. Now what happens? This will be open circuit. This will be open circuit. This will be open circuit. This will be open. For 0 it will be off. For 1 it will be on. Open circuit. Then output voltage equal to 1. So 1 output. So this may be happen like it is a inverter, like it is designing, inverter designing. It is a pull up is nothing but PMOS transistor. Pull down is NMOS transistor. 1 we are applying, it is 0. 0 we are applying, output is 1. Okay. What happened? We are applying a common input, means any single input. It may be 0 or 1 input. 0 or 1 input. Okay, 0 or 1 input. 1 we are applying, output is 0. 0 we are applying, output is 1. So the large number of fan-ins we are using. Large number of fan-ins we are using. So same common input is applied. Common input is applied. This is output 1 detection. Output 1, input also 1 input. 1 input. We can also design like this. All the gates can be designed by MOS transistors. MOS transistor is a gate level design. So we can design this AND gate by using this MOS transistors. Okay, right? This is about 0-1 detection. So let me again explain this. Used large number of, it will be asked in examination. We can 0-1 detection, large number of inputs, zeros or ones. Okay, more number of fan-in. Okay, and more number of fan-ins. It may be used 16 or 32-bit, 64-bit data inputs. Effective hardware design and speed increase, low power design, right? Is a gate level design, and we are seeing this one in MOS transistor level design, parallel connections and series connections. Okay, so pull up pull down ratio pseudo NMOS is 3/1. By using this pseudo NMOS, this is pseudo NMOS design. So this is pseudo NMOS design. Pseudo NMOS 0-1 detection, 0-1 detection. The circuit below is pseudo NMOS design detection. So pseudo NMOS design, the pull up pull down ratio is 3/1. So it is less than this 4/1 of 4/1. 4/1 if you are using depletion is NMOS. If you are using depletion NMOS, so depletion NMOS, it is 4/1. Okay, but whereas PMOS is used, pull up pull down ratio is 3/1. So this is 3/1 and it is 1/1 ratio. All are 1/1 ratio. All are 1/1 ratio. Okay, so it is 3/1, it is 1/1 ratio. Where instead of NMOS depletion, we use PMOS depletion. Pull up pull down ratio is reduced. Okay, and speed of operation increase, power also less power by using this 0-1 detection. Okay, thank you. Please subscribe our channel, inform to your friends. Thank you.